Section 4.2 is on sigma notation. Sigma looks like this. It's a giant Greek letter. The notation we use, whatever down here at the bottom is going to tell you the starting value. So in this case, the first value we're going to plug in for I is 1. This here's the rule. That's where we're plugging it in. And then this value up at the top here is telling you the last value to plug in. So when we're evaluating this, I equals 1 to 6 of I squared minus 4. So we start with I equals 1, so we plug in 1 for I, and we get -3. And then we plug in 2 for I, and we get 0. Plug in 3 for I, gives us 5. 4 gives us 12. Plug in 5 for I, gives us 21. Plug in 6 for I, gives us 32, and we stop there because 6 was the top one. That's the last value we plug in. And then sigma, the giant sigma, tells us to sum it, to add it up. So we add those values up. And we get 53, 58, 70, 67. You do have a way to do these on the calculator. There's a couple different ways to do it. The fastest way to do it is to push alpha trace, nope. Alpha zoom, nope. Alpha window, there it is. Alpha window will pull up this screen right here and scroll down to number 2, which is the sum symbol. And then you can say, you could use I. Don't use this I down here. That's the imaginary number I. I usually just use X because it's right on the main screen here and you don't have to push a couple buttons. So X equals 1 to 6. And since we used X instead of I, we have to use X again here. X squared minus 4. And we do indeed get 67. Plugging the values in works fine if you have like 1 to 6, but if that's 1 to 52, nobody's going to have to plug in all 52 numbers. So you could use your calculator, but she'll want you to use these properties occasionally. So there are 4 summation properties. The first is if I am summing starting at 1 and going up to n of C, any constant, if this is just a number. So like if this looked like I equals 1 to 8 of 3. So the answer is going to be the constant times n, and n in this case would be 8. So you would get 24. If we have the sum, I starts at 1 and goes to n of I, the formula that can be used is n times n plus 1, all divided by 2. And so on. I squared and I cubed have these 2 formulas here. So take a minute, pause the video, and write down those 4 rules, and then you can start her up again. So example 2 asks us to use the properties of summation to evaluate the sum of the sum as I goes from 1 to 20 of 2i squared. So because it's I squared, we're going to use the rule that has an I squared in it, which is this one here. So it's n times n plus 1, so n times n plus 1 times 2n plus 1 all over 6. Those formulas will be given to you on the test. The 2 right here can just stay out in front. So we replaced I squared with the formula for I squared. Then you can plug the 20 in for n's. So we have 2 times 20 times 20 plus 1 times 2 times 20, 40 plus 1, all over 6. And then it's calculator time. And we get 5,740. And again, you should have a good idea if that's right or not by using the summation on your calculator. You could type it in here just to confirm from 1 to 20 of 2i squared. And we get the same answer, 5,740. Part B asks for the sum as I goes from 1 to 15 of I minus 1 squared. I minus 1 squared. So we're going to need to expand I minus 1 squared. So if we square that binomial, we should get I squared minus 2i plus 1. If you're not sure, go ahead and write it out twice and FOIL it. I squared, we should be able to replace with the I squared formula, which is n plus 1, 2n plus 1, all over 6. Then we've got minus 2 times I. I we can replace with the formula for I, n plus 1 over 2. And then the plus 1, 1's just a constant. So for the constant, we take whatever that constant is, 1 times n. 1 times n. Replace the n's with 15. Two times 15. And evaluate. 15 times 16 times 31 all over 6. Plus 30 times 16 over 2. Plus 15. 1,495. And again, you can verify it on your calculator. One thing you need to be careful about, don't type it in like this. Notice my answer is wrong. Notice what it's doing. Inside the parentheses here is whatever it wants you to sum. So you are summing x minus 1 from 1 to 15. And then when you type in the squared, so it's doing all this first, getting an answer, and then squaring it. So if you are going to type this one into your calculator, you want to go x equals 1 to 15. And then inside the parentheses should be all this right here. So you need parenthesis x minus 1 squared. You need to make sure that squared is inside this sum there. And it should give us, uh-oh, it's not 1495, huh? What did I mess up? All right, I found my mistake. It's right here. It's the dumb one. When I type this into my calculator, that should be a minus sign right there. Minus. Hey, there we go. 1015. 1015 is correct. Not that. Sorry about that. Moving on. Example 3 asks us to evaluate the sum as I starts from 1 and goes up to 12. of I times the quantity I squared minus 1. You're going to do this one on your own here in a minute. The very first thing you need to do, you cannot use the I rule and then the I squared rule and multiply them together. So kind of like the last one when we expanded it first, the first thing you need to do is distribute the I, and then you can use the I cubed rule in the I. So go ahead, you pause the video, finish this one, see if you got it right or not, and then you can start it back up. The rule for I cubed is n squared times n plus 1 squared over 4. So we've got n squared times n plus 1 all squared all over 4. And then we've got minus I, the I rule, n plus 1 over 2. N is 12, so plug in 12. And type that into your calculator, hopefully correctly this time. Nope. And I get 6006. Which is indeed the correct answer. 6006. Example 4. We're going to take this a couple steps further here. This one looks similar. It just has these n's on this side also. So the sum as I starts at 1 and goes up to n of I over n cubed times 1 over n. So the first thing we're going to do is we're going to simplify this. And we're going to go, the sum is I starts at 1 and goes to n of I cubed over, notice I've got I cubed over n cubed, and then I've got another n on the bottom. So I've got n to the 4th. From there, we want to replace I cubed with the I cubed formula, which is n squared times n plus 1 squared over 4. So I replaced I cubed with the formula, and this n to the 4th is just going to stay on the bottom. And then we can expand this. N squared plus 2n plus 1. And distribute that n squared. And notice we don't have a value to plug in for n, so we're just going to leave it like that. That's our answer. Part B. Oh boy. This is a big one. The sum as I goes from 1 to n of 4 minus the quantity 1 plus I over n squared. All that times 1 over n. So the first thing we need to do is we want to distribute this. We need to simplify in here first. So we're going to FOIL this part out. You can write it out twice and FOIL it, or remember the rule. So we've got 1 plus I over n plus I over n. Oops. Plus I squared over n squared is that last term. So if I combine up these like terms, I've got 1 plus 2I over n plus I squared over n squared. Distribute your minus sign here. So I've got 4 minus 1. Go ahead and combine those. Minus 2I over n minus I squared over n squared. And distribute this 1 over n. So I've got 3 over n minus 3I over n on the bottom, and n on the bottom is n squared on the bottom. And here I've got n cubed on the bottom. Next thing we're going to do is use the rules. So 3 over n, remember n's just a number, so this is a constant. So we're going to use the constant rule, which is just that constant times n. Here I've got I can replace I with its rule, which is n times n plus 1 over 2. So I replace the I with this n plus 1 over 2, the 3 I just left on top, the n squared I just left on the bottom. And the I squared, I need to replace it with its rule. I squared rule is n plus 1, 2n plus 1 over 6. n plus 1, 2n plus 1. All over 6. I'm going to leave that n cubed on the bottom. So I've got 3 out front here. This n cancels with one of these n's. And then I'm going to distribute that 3. So I've got 3n plus 3 over 2n. This n right here can cancel with one of these. And I'm going to leave that in the factored form. That's fine. N plus 1 times 2n plus 1 over 6n squared. And that's a fine answer for now, at least. All right, one more thing we need to do with this. This problem is the exact same problem that we just did. We've just added this part right here. So this we already did. Now we're evaluating the limit as n approaches infinity. Most of the time the problem will look more like this than the previous example. We just kind of broke it down step by step. So the first thing you would do is you would do all this work, which is what you just did on the previous example. So all of this work gets me this guy right here. So n to the 4th plus 2n cubed plus n squared over 4n to the 4th. And we need to evaluate the limit as n goes to infinity. Back in section 3.5, we learned how to evaluate the limit as n goes to infinity. We look at the exponent, the highest exponent on the top, 4, the highest exponent on the bottom, 4. And if they're equal to each other, we divide the leading coefficients, 1 divided by 4. This one, just like part B that we just did, again, we're adding this limit as n approaches infinity. So the first thing you would do is all that work that we did in the previous example. And that got us down to this guy right here. So right now we're at that step right there. And now we need to evaluate the limit as n approaches infinity. Because we're adding and subtracting things, we are just going to bring down the 3, bring down the minus sign, and evaluate the limit as n approaches infinity of this, which is 3/2. This here, we at least need to think about what the highest power on the top would be. If we FOILed this out, we would get 2n squared, and then we'd have plus 3n plus 1, but that doesn't really matter. So the highest power on the top is 2, bottom is 2, so we divide the leading coefficients. We get 3, let's see here, get a common denominator. Gives us 9/7/6. So that is section 4.2. I know there's kind of a lot in there. Shoot me an email if you're having any questions. I'll get back to you when I can.